question has followed me for most of my scientific life, and it has a simple shape, yet an unsettling depth. How can something made of nothing but warped space-time become one of the most powerful entities in the universe? A black hole contains no matter in the conventional sense, yet it governs stars, deflects light, and reshapes the geometry around it with quiet certainty. I still remember the first time I watched a gravitational wave signal rise on a screen. The room was silent in the way laboratories become silent when everyone understands the magnitude of a moment. The signal was faint, lasting less than a heartbeat, but it carried the imprint of two black holes that had collided more than 1 billion years ago. One truth has grown more striking with time. The universe contains events so powerful that for a brief instant they outshine all the stars combined, yet they leave behind no light at all. In the next hour, I'd like to take you through this warped side of the universe. Its black holes, its gravitational waves, its speculative bridges, and the open questions that still shape the frontiers of physics. When I look back to the early decades of modern relativity, I often think about how quiet the theoretical landscape was compared with today. Many of the ideas that now appear in textbooks, black holes, gravitational waves, wormholes, existed only as mathematical curiosities. When I first encountered them, they felt more like exercises carried out on chalkboards than descriptions of real things in the cosmos. Yet those exercises carried a sense of direction. They suggested that space-time was not a passive stage, but an active participant in the universe. Still, almost no one could say with confidence whether the equations were pointing toward genuine phenomena or toward elegant illusions born from mathematics. I remember the way my mentors described this period. John Wheeler, who shaped much of my early thinking, had an unusual ability to draw meaning from abstract structures. He spoke of collapsing stars as if they were characters in an unfolding cosmic drama, and he treated the curvature of space-time with the same familiarity that an architect brings to the contours of a building. But even Wheeler emphasized how little was actually known. In lectures, he would outline the theoretical signatures of a black hole, yet after the equations were written, he would pause and acknowledge that no telescope had ever confirmed such an object. The conversation would drift towards speculation, because at the time, speculation was unavoidable. In those years, many of the central questions were embarrassingly simple. Do black holes really exist, or are they merely solutions to Einstein's equations? If the universe began in a singular state, can any trace of that moment still be found today? Are gravitational waves physical, or are they mathematical artifacts? The best physicists of the mid-20th century debated these questions vigorously, and their disagreements shaped the first generation of research on warped space-time. It was not unusual for one group to argue that gravitational waves carried real energy, while another argued that they were coordinate effects with no physical meaning. Without observational tools, the arguments sometimes circled endlessly. You might imagine that this uncertainty led to frustration, but in my experience, it bred a different kind of curiosity. When evidence is scarce, thought experiments become central. This is why early explorations of warped space-time often relied on analogies: a stretched rubber sheet, a bead sliding along a distorted surface, a beam of light bending where no force appears to act. These analogies were not literal, they were attempts to create intuition in a field where intuition was not naturally available. Looking back, they provided the scaffolding that allowed later discoveries to be interpreted correctly. As I began my own research, I realized that part of the challenge came from our tendency to think of space and time as fixed. Everyday experience guides us toward the belief that geometry is stable. Measuring a table, watching a ball fall, or tracing the path of a beam of light, all these activities reinforce the sense that the stage of the universe never changes. Einstein's theory overturned that assumption. It suggested that geometry could stretch, twist, or ripple, and that these distortions could have physical consequences. Yet without direct evidence, the theory remained suspended between imagination and reality. I often think of those early speculations as the quiet groundwork for everything that followed. Without the confidence to explore extreme consequences of Einstein's equations, there would have been no predictions about gravitational collapse, no models of neutron stars, and no pathway to understanding how space-time behaves under the most intense conditions nature can produce. Even ideas that now sit at the edges of accepted physics, wormholes for example, were kept alive because the community allowed room for well-reasoned exploration, even without immediate confirmation. The absence of evidence also shaped how I learned to approach scientific questions. When I read early papers on gravitational waves, I noticed how carefully their authors separated what was known from what was assumed. That discipline became invaluable decades later when observational astrophysics began to produce data of unprecedented precision. It taught me that a lack of evidence is not a verdict. It is an open invitation to think more clearly. As you listen to these ideas, you and I share something with those earlier generations of physicists, the sense of stepping into a landscape built from both observation and imagination. Today we are fortunate to have tools that they did not. Interferometers, sensitive enough to detect changes smaller than an atomic nucleus, radio telescopes capable of imaging the environment near a supermassive black hole, but the foundational questions remain deeply human. What is space? What is time? And how far can the equations of physics be trusted? Curiosity about curved space-time often begins with a simple realization. Our senses are poorly equipped to perceive geometry when it bends. Everyday motion feels linear, distances seem fixed, and the world appears to rest on a reliable three-dimensional scaffold. Yet the more deeply I studied Einstein's theory, the more I understood how misleading that comfort can be. Geometry, at its core, is dynamic. It responds to mass and energy, and it shapes the motion of everything within it. A useful way to build intuition starts with a familiar object. Picture a child's trampoline stretched tightly across its frame. Set a heavy object at the center and the surface bends downward. This distortion guides the paths of smaller objects rolling nearby. They do not fall because a force pulls them inward. Instead, they follow the easiest route across a curved surface. Physicists call this a geodesic, the straightest possible path through a bent geometry. Although the analogy is imperfect, real space-time curves in 4 dimensions, not 2, it helps create a mental picture before tackling the full idea. Another image comes from something quieter, walking across a slightly sloped field. A person who pays attention to the ground underfoot notices that each step subtly changes direction to stay on the easiest path. Our brains correct for these shifts automatically. In relativity, motion behaves in a similar way. Objects respond to space-time's shape even when that shape is invisible to our senses. Gravity becomes not a pull, but a natural response to the terrain of space-time. I remember the first time I examined the mathematics behind a non-rotating black hole. The equations described a curious property. The circumference measured around the equator and the distance measured straight through the center did not align with Euclidean expectations. If you traveled along the diameter, the actual path would be longer than intuition suggests. A flat sheet would never behave this way, but curved geometry can. Astronomers later used this insight to refine their understanding of how black holes influence light, particle orbits, and the behavior of nearby stars. Insights like this gain clarity when translated into plain language. Imagine a sheet of fabric pushed so deeply that the central region becomes funnel-shaped. An ant trying to cross from one side to the other encounters a much longer route than a viewer above the fabric might expect. The same principle applies to a slice through a black hole. From far away, space seems flat. Closer in, the distance between 2 points grows because the geometry is stretched. Nothing exotic is required, only the recognition that space itself can warp. Some listeners wonder whether such distortions have any relevance to life on Earth. A closer look at GPS satellites offers an answer. Each satellite carries an atomic clock, and its ticking rate differs from clocks on Earth because space-time is slightly less curved at orbital altitude. Engineers must correct for this difference daily. Without those corrections, navigation errors would accumulate quickly enough to disrupt everything from aircraft guidance to ordinary smartphone maps. Even gentle curvature, therefore, carries measurable consequences. Another everyday link emerges from the path of light. Starlight traveling near a massive object bends slightly, causing the object to act like a lens. The effect was famously confirmed during the solar eclipse of 1919, when expeditions led by Arthur Eddington measured the apparent shift of background stars as their light passed near the sun. Those measurements provided some of the earliest observational support for general relativity. A century later, the same principle underlies powerful observatories, such as the Hubble Space Telescope and the Atacama Large Millimeter Array. These facilities routinely observe galaxies magnified and distorted by gravitational lensing, revealing structures that would otherwise remain invisible. Geometry becomes even more interesting around spinning black holes. Their rotation drags space-time along, creating a swirl that resembles water spiraling toward a drain. This dragging affects how distances and directions behave near the horizon. The mathematics describing it can appear abstract, but a clearer physical picture comes from rotating a bowl of water. Leaves floating near the center move quickly. Those near the edge move slowly. In relativity, space-time plays the role of the water, and anything nearby, including beams of light, must respond to its motion. None of this requires mastery of equations. What matters is the awareness that geometry is active. Space stretches, time slows, and light follows paths that emerge from the underlying curvature. Every observation of gravitational lensing, every satellite timing correction, and every simulation of a black hole relies on this central principle. Modern astrophysics depends on instruments capable of detecting tiny distortions, yet the ideas guiding those measurements grew from simple analogies. Those analogies still help me clarify concepts when I speak about warped space-time. They connect the abstractions of general relativity to physical experiences you already understand, even if you rarely think of them as geometric. A clearer understanding of black holes often emerges not from grand images, but from quiet thought experiments. Imagine setting aside the dramatic scenarios usually found in movies and focusing instead on a single steady line of reasoning. What happens to the flow of time as you drift inward? The question sounds narrow, yet its answer reshapes almost everything we believe about motion, distance, and causality. Time behaves differently near a black hole, and the first hint appears long before anything extreme happens. Picture an astronaut monitoring a small atomic clock on her wrist while slowly approaching a massive compact object. Every tick seems normal to her. Nothing feels altered. Meanwhile, an identical clock far away records each second with a slightly different rhythm. The disagreement grows not because either clock malfunctions, but because the underlying geometry hosting them changes. Space and time are intertwined, and curvature alters the pace at which time unfolds. Signals sent outward reveal this divergence more vividly. Radio pulses leave the astronaut spacecraft cleanly, yet each pulse reaches distant observers with increasing delay. It is tempting to interpret this as interference, as though the environment were blocking the signal. But nothing obstructs it. The waves simply must traverse a region where time runs more slowly. The pulses stretch, their sequence becomes uneven. Eventually, the astronaut's final message appears almost frozen, suspended at the threshold of what physicists call the horizon. Inside the spacecraft, none of this slowing is felt. That contrast, the calm inside and the distortion observed from outside, is one of relativity's most striking predictions. A horizon is not a surface. It offers no physical resistance, no impact, no sudden force. The ship glides through as though crossing an invisible boundary between two regions of the same ocean. The difference lies in the future paths available. Outside the horizon, a traveler can choose trajectories that lead outward. Once inside, those routes vanish from the geometry. Every possible direction bends toward the center. Light offers an intuitive way to visualize this transition. Far from the black hole, light cones, representations of all possible directions light can move, tilt gently inward. Closer in, they lean more steeply. At the horizon, the tilt becomes total. Even beams aimed outward align with the inward pull created by curvature. This shift is not metaphorical. It is a structural change in space-time itself, revealed by the paths light is allowed to take. Travelers falling into a supermassive black hole, such as the one near the Milky Way's center, would experience this environment with surprising smoothness. The gravitational gradient across the body, often called tidal force, remains modest at the horizon because the black hole is so large. That doesn't diminish the underlying physics. It simply changes the way the fall feels. Smaller black holes compress the same curvature into a much tighter region, amplifying those gradients dramatically. Whether the journey is gentle or violent depends largely on mass. Deeper inside, the geometry intensifies. Directions lose the meaning they had outside. Motion towards the center becomes as unavoidable as moving forward in time. The traveler might fire engines in an attempt to escape, yet no thrust changes the essential fact. Space-time directs every possible future towards the singularity. The comparison to a river becomes useful here. On calm waters, a strong swimmer can choose any direction. Near a waterfall, even the strongest swimmer is carried over the edge. In a black hole, there is no edge, only a restructuring of space-time that offers no upstream. Physicists remain cautious when describing the final approach toward the singularity. General relativity offers reliable guidance until curvature becomes extreme, but the theory falters when distances shrink to scales governed by quantum mechanics. This region invites new physics. A future theory of quantum gravity will almost certainly revise the classical picture, perhaps removing the singularity altogether. For now, its presence marks a boundary where scientific language becomes humble. One reason these ideas matter lies in how widely their principles apply. Time dilation, for instance, occurs not only near black holes, but near any massive body. Earth's surface has slightly slower time than its orbit, a fact essential for global positioning systems. Without correcting for gravitational time dilation, satellite navigation would drift rapidly, rendering it unusable. In that sense, understanding what happens near a black hole clarifies everyday technology. Even gravitational wave astronomy depends on the physics of horizons and infall. When two black holes spiral together, their horizons distort and merge. The resulting vibrations in space-time, the gravitational waves recorded by LIGO, are direct signatures of this process. Observing them provides a form of listening to the fall, not of a spacecraft, but of two objects collapsing into a single, deeper well of curved space-time. Patterns in nature often reveal themselves through motion. A stirred cup of tea forms spirals. Clouds above a storm rotate in great arcs. Even the water circling a small drain shows how rotation organizes flow. Concepts like these gave me my earliest intuition for something far less familiar: the way a spinning black hole drags space-time into a slow whirl around it. Instead of treating rotation as a detail, general relativity treats it as an architect. Spin does not merely modify a black hole, it reshapes the arena around it. One of the clearest windows into this idea comes from a phenomenon known as frame dragging. The name may sound technical, but the physical picture is surprisingly approachable. Picture a heavy sphere suspended in thick syrup. Turn the sphere gently, and the syrup near its surface begins to rotate as well. The motion spreads outward, growing weaker with distance. Replace the syrup with space-time and the rotating sphere with a spinning black hole, and you have an initial sense of what relativity predicts. The difference is that space-time has no viscosity and offers no resistance. Its response is geometric rather than fluid-like, but the analogy captures the behavior. Space-time is forced to twist. Evidence for this twisting exists close to home. NASA's Gravity Probe B mission, launched in 2004, used ultra-precise gyroscopes in Earth orbit to measure how our planet drags space-time as it spins. The effect was extremely small, a shift in the gyroscope's orientation amounting to a tiny fraction of a degree per year, but the mission detected it. If a rotating planet produces such a distortion, a rotating black hole produces one vastly stronger. Imagine drifting near such an object. The moment you switch off your engines, your motion is no longer yours alone. Even if you aim to hover above the rotating black hole, the surrounding space-time gently nudges you sideways. You are carried, not because of wind or magnetism, but because the very stage beneath you is turning. This region, often called the ergosphere, sits outside the horizon and has a distinctive property. Everything inside it is compelled to rotate. No object, not even a beam of light, can remain fixed relative to the distant stars. Observers trying to understand this behavior often ask whether the twisting resembles a tornado drawing matter inward. The answer is more subtle. A tornado pulls, a rotating black hole guides. The difference matters. In the black hole's environment, the twisting emerges from geometry rather than pressure or force. Space-time itself acquires a directional preference, and anything embedded within it moves accordingly. Simulations help make this more tangible. When two spinning black holes orbit each other, the vortices of twisted space-time interact. You might picture two whirlpools meeting on a turbulent lake. Each has its own swirl direction and structure, and as they approach, the patterns stretch, buckle, and sometimes merge into unexpected shapes. Numerical relativity, an approach that solves Einstein's equations using powerful supercomputers, has revealed intricate behavior in these interactions. Some simulations show one vortex wrapping around another. Others show temporary bridges forming between regions where space-time twists in opposite directions. Such details are not merely decorative, they determine the form of the gravitational waves emitted during the final moments before merger. These waves carry the imprint of the black holes' spins and the dynamics of their warped environment. The detectors at LIGO, Virgo, and later CAGRA identify these subtle features in the incoming signals. When I speak with colleagues who analyze gravitational wave data, I often hear them describe spin signatures as fingerprints. Their patterns help distinguish one black hole system from another. Another consequence of rotation emerges from the way light behaves. Rays skimming the ergosphere follow tight arcs, bending more dramatically on the side where rotation aligns with their motion. This asymmetry produces a striking effect in images of accretion disks, the glowing rings of superheated gas that surround many black holes. One side of the ring appears brighter, not because the gas intrinsically emits more light, but because rotation boosts the intensity of photons moving in the same direction. Observations from the Event Horizon Telescope show this brightness asymmetry in real galaxies, including the black hole at the center of M87. It is one of the cleanest confirmations that space-time twisting is not just a theoretical construct. The possibility of extracting energy from rotation adds another layer of fascination. In the late 1960s, Roger Penrose suggested a mechanism, now known as the Penrose process, through which an object entering the ergosphere could split in two. One piece falls into the black hole, the other escapes with more energy than the initial object carried. Although difficult to realize in practice, The principle inspired later models of astrophysical jets, long focused beams of particles ejected from the poles of some black holes. Observatories such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have traced these jets across thousands of light years, suggesting that rotation helps organize the energy that powers them. Conceptually, the twisting of space-time invites a shift in perspective. Instead of treating space as a quiet container, we see it as an active participant, capable of rotating, stretching, and responding to mass and motion. Even the simplest picture of a spinning black hole becomes richer once this dynamic background is acknowledged. Understanding these behaviors does not require advanced mathematics. It requires only patience and a willingness to let geometry replace instinct. Rotation shapes space-time in ways that challenge familiar experience, yet the evidence supporting this view has grown steadily. Satellites detect it around Earth, telescopes observe it around supermassive black holes, simulations reveal its complexity during mergers, and gravitational waves carry its signature across billions of years. Images of black holes often begin with darkness, yet the most revealing features come from light itself. Light carries information about curvature, motion, and the hidden structure of the spacetime it passes through. Before the first direct image of a black hole was released by the Event Horizon Telescope, much of what we believed about their appearance came from carefully built models rooted in Einstein's equations. Those models taught us something essential. A black hole is not simply a dark sphere. It is an optical engine, sculpting the trajectories of photons in ways that no ordinary object can reproduce. A useful way to approach this is through the idea of gravitational lensing. When light passes near a massive body, its path bends. We observe this throughout the cosmos. Distant galaxies magnified by intervening clusters, stars appearing shifted during solar eclipses, and faint arcs stretching across deep-field images taken by the Hubble Space Telescope. These effects arise because space-time curves around mass. A black hole being an extreme concentration of mass and curvature pushes this principle to its limit. Picture a single star positioned behind a black hole from your point of view. Several distinct paths exist for the light leaving that star. One path travels near the black hole's edge and arrives almost directly. Another swings around the back before curving outward again. Yet another wraps around multiple times, like a thread circling a spool. Each route produces a separate image. To an observer, the star appears in several places at once, though all those appearances originate from the same source. Astronomers call these structures relativistic images, and they cluster close to a boundary known as the photon ring. The photon ring itself is not a solid feature. It is the result of light that narrowly avoids capture. Photons passing extremely close to the black hole orbit once, twice, or many times before escaping. Each loop amplifies their brightness slightly, but the amplification is modest. The real significance of the ring lies in what it reveals about geometry. Its diameter, thickness, and brightness are governed by the curvature near the horizon, and thus offer a form of measurement. When the Event Horizon Telescope collaboration published the first image of M87's supermassive black hole in 2019, the bright ring encircling the dark shadow provided confirmation that the models built from general relativity were fundamentally correct. Accretion disks complicate the picture in fascinating ways. Gas spiraling toward a black hole heats to extraordinary temperatures, emitting light across the electromagnetic spectrum. X-ray observatories such as NASA's Chandra telescope capture this radiation, revealing turbulent patterns in the disk. Because of the strong curvature nearby, light from the backside of the disk bends around and reaches the observer. The result is a view in which both the front and back surfaces appear simultaneously. To someone encountering this for the first time, the sight seems impossible, like looking at both sides of a coin without flipping it. Rotation adds further asymmetry. Gas moving towards the observer experiences a boost in brightness due to special relativistic effects, while gas moving away appears dimmer. This contrast creates a bright crescent on one side of the ring. Such features were predicted decades before telescopes could detect them. The agreement between theory and observation is striking, especially given the complexity of the environment. Another feature often overlooked is the shadow. The dark region in the center of a black hole image is not the horizon itself. It is a projection, the set of directions from which no light can reach the observer, because every possible photon path is drawn inward. The shape and size of the shadow carry information about the black hole's mass and spin. Even subtle distortions encode details about the underlying geometry. Although the Event Horizon Telescope's resolution softens these features, future instruments, particularly space-based arrays, may render them with far greater clarity. Visualizations created for research and for films also reveal the intricacy of light paths. During work on the movie Interstellar, simulations were produced using full relativistic ray tracing. Those simulations used equations derived from general relativity to trace the exact routes photons would follow near a spinning black hole. The resulting images surprised even scientists familiar with the theory. Layers of the accretion disk folded over each other in unexpected patterns, and the bright crescent formed naturally. These simulations offered the public a glimpse of how space-time manipulates light, and they helped refine some aspects of scientific visualization. Human perception plays its own role here. Light near a black hole can be extraordinarily bright, but the eye responds non-linearly. Even cameras introduce distortions. In scientific contexts, researchers compensate for these limitations with calibrated instruments. In artistic contexts, choices must be made about how much to reveal and how much to soften. The goal is not to create a perfect representation, but to convey the underlying physics faithfully. Observations continue to evolve. The Event Horizon Telescope now compares images across multiple wavelengths, revealing how magnetic fields structure the flow of gas near the horizon. These measurements help explain how some black holes launch high-energy jets, streams of matter and radiation extending thousands of light years. Although not directly related to the visual appearance, jet formation depends on the same relativistic environment that shapes the photon ring. Understanding how black holes bend light is not just an exercise in visualization, it is a method of measurement. Each distorted arc, each bright crescent, each shadowed region provides data about mass, spin, and the curvature of space-time. By interpreting these signatures, astronomers can test general relativity under conditions impossible to reproduce on Earth. Most of what humanity has learned about the universe has come from light. Telescopes, no matter their size or wavelength, rely on photons arriving from distant places, yet there exists another messenger, one that does not care about dust clouds, does not scatter, and does not fade as it travels. Gravitational waves carry information not through particles, but through the shifting geometry of space-time itself. Long before detectors existed, the idea sounded almost abstract, the sort of prediction that might remain untested for generations. Still, the equations pointed insistently toward their existence. Exploring the concept begins with a familiar experience, dropping a stone into a still pond. Circular ripples move outward, carrying the disturbance across the surface. Gravity, in Einstein's framework, replaces the pond with space-time. When massive objects accelerate, especially in spiraling pairs, the curvature around them changes rhythmically. Those changes propagate outward at the speed of light, forming waves that stretch and squeeze the space they pass through. The deformation is unimaginably tiny by the time it reaches Earth, far smaller than atomic dimensions, yet still real. Evidence for gravitational waves appeared indirectly before any direct detection. In the 1970s, radio astronomers Russell Hulse and Joseph Taylor studied a pair of neutron stars orbiting each other. Their timing measurements, made using the Arecibo Observatory, showed the orbit shrinking at exactly the rate predicted if the system were losing energy through gravitational waves. The match between observation and theory earned them the Nobel Prize in 1993. Even so, these signals were not waves measured on Earth. They were deductions from orbital behavior. The community still sought a way to detect the waves directly. Understanding why direct detection is so difficult calls for a sense of scale. Two neutron stars or black holes could collide with more power than all the stars in the universe emit during the same moment, yet the resulting waves distort local distances by only a fraction of a proton's diameter by the time they reach us. Any detector must remain stable enough to sense variations that's small while isolating itself from environmental noise, traffic vibrations, seismic motion, temperature shifts, even quantum fluctuations in the measuring instruments. Researchers eventually converged on a technique known as laser interferometry. The essence is conceptually simple. Split a beam of laser light into two perpendicular paths, reflect them from mirrors several kilometers apart, and recombine them. If a gravitational wave passes, one arm lengthens while the other shortens, altering the pattern created as the beams meet again. Engineers and physicists spent decades refining this idea. The mirrors had to hang in vacuum chambers. The lasers needed extraordinary stability. The entire structure required isolation systems capable of damping vibrations smaller than anything felt or heard. During the early development of these detectors, many scientists questioned whether the effort could succeed. The required sensitivity seemed almost beyond reach. Even after technological innovations accumulated, better coatings for mirrors, improved suspension systems, active noise control, success was not guaranteed. Yet each incremental improvement brought the idea closer to reality. Collaborations grew. MIT and Caltech in the United States, the Max Planck Institutes in Germany, groups in the United Kingdom, Italy, France, Japan, and Australia. The project became global because no single institution could shoulder the technological and analytical challenges alone. Gravitational waves differ from light in a deeper sense as well. They carry information about regions where light cannot escape, the interiors of merging black holes, the dense cores of neutron stars, and perhaps one day the earliest epochs of the universe. Where light offers surfaces and spectra, gravitational waves offer motion. Motion encoded not in particles, but in the shifting geometry of space-time. A signal captures the rhythm of an orbit, the crescendo of a merger, and the fading ring-down of the final remnant. Interpreting these signals requires precise modeling. Supercomputers solve Einstein's equations to generate templates of what the waves should look like for different masses, spins, and orbital configurations. Analysts compare incoming data to these templates, searching for matches that reveal the properties of the distant system. This approach, called matched filtering, transforms the faint oscillations recorded in the detectors into detailed astrophysical information. The masses of the objects involved, the distance to the merger, and sometimes even the alignment of their spins. One of the transformative strengths of gravitational waves is their immunity to many forms of obstruction. Light from a distant galaxy can be absorbed by dust clouds. X-rays can be blocked. Radio waves can scatter. Gravitational waves, however, pass through intervening matter almost unchanged. This allows us to observe events hidden behind dense gas or deep within regions where electromagnetic radiation cannot escape. When gravitational and electromagnetic observations are combined, as they were for the neutron star merger detected in 2017, the resulting picture becomes far richer than either method alone. Gravitational waves also open a way to test general relativity under extreme conditions. Their shape, frequency evolution, and damping all reflect the underlying geometry. If space-time behaved differently from Einstein's predictions, the discrepancies would appear in the signals. So far, the matches have been consistent. No alternative theory has yet displaced general relativity in this domain, though scientists continue to search for small deviations that might guide future breakthroughs. As we move deeper into gravitational wave astronomy, it becomes clear that these waves are more than exotic phenomena. They are a new language for exploring the cosmos. Light tells us how objects shine. Gravitational waves tell us how they move, collide, and shape the space-time around them. Each method fills gaps the other cannot reach. Together, they form a more complete picture of the universe, one in which motion and illumination, geometry and radiation work in quiet partnership. Large scientific instruments rarely begin with clarity. They begin with doubt, ambition, and a sense of scale that feels unreasonable at first glance. LIGO, the Laser Interferometer Gravitational Wave Observatory, followed that path from its earliest conception. The idea was simple enough on paper: measure distortions in spacetime far smaller than anything previously attempted. Yet simplicity on paper often conceals the scale of work required to turn a concept into reality. The earliest version of the idea emerged in the 1970s, when Rainer Weiss at MIT outlined the basic principles of an interferometer capable of sensing gravitational waves. His design involved two long arms arranged at right angles, with laser light bouncing between suspended mirrors. A passing gravitational wave would stretch one arm and compress the other, shifting the light's interference pattern. When Weiss first presented these ideas, many physicists, including me, hesitated. The predicted signals were so small that it seemed unlikely any technology could achieve the required stability. Doubt did not stop the work. Weiss, along with colleagues at MIT, Caltech, and later other institutions, began identifying every source of noise that could mask a gravitational wave signal. Seismic vibrations, thermal fluctuations in mirror coatings, quantum noise in laser light, and even the minute bending of the Earth's crust. Each required a solution. Mirrors needed to hang from multiple layers of suspension, isolating them from ground motion. Vacuum chambers needed to stretch for kilometers, eliminating air currents. Laser systems needed unprecedented stability. It became clear that no conventional laboratory could house such a device. Caltech joined MIT as a central partner, and the United States National Science Foundation committed to supporting a project of unprecedented scale. The design evolved from the initial concept into a dual-site observatory, one set of arms built in Hanford, Washington, and another in Livingston, Louisiana. Two detectors were essential because any true gravitational wave would appear in both with a calculable time delay, while local disturbances like trucks, thunderstorms, or small earthquakes would not. During the 1980s and 90s, the collaboration expanded internationally. The Max Planck Institute in Germany contributed expertise in laser stability and quantum optics. Universities in the United Kingdom, particularly Glasgow, pioneered suspension systems and mirror technologies. Groups in Italy, France, Japan, and Australia joined the global effort. Although the observatories were built on American soil, the project quickly became a multinational enterprise. Without this collective work, the required precision would have remained out of reach. Construction challenges matched the scientific ones. Vacuum tubes 4 kilometers long had to maintain pressures 1 trillion times lower than atmospheric levels. Mirror surfaces needed polishing so finely that imperfections smaller than a fraction of a wavelength of light were unacceptable. Engineers devised active systems capable of sensing Earth's subtle tremors and cancelling their effects. Even after these systems were built, they required constant tuning. Instruments this sensitive drift out of alignment easily, and the detectors needed months of careful adjustments before they achieved stable operating conditions. In the early 2000s, LIGO's first generation, called Initial LIGO, began searching for signals. Although it reached its design sensitivity, no gravitational waves were detected during that phase. The outcome was expected. Initial LIGO served as a technological foundation, demonstrating which ideas worked well and which required improvement. The next step, Advanced LIGO, would push sensitivity roughly 10 times higher, extending the volume of the observable universe by a factor of 1,000. The upgrade was transformative. New lasers produced cleaner beams, and new mirror coatings reduced thermal noise. Suspension systems improved, enabling the mirrors to remain stable despite ground motion. Advanced LIGO became operational in 2015. Even then, many of us anticipated months of engineering runs before the first real observation. The detectors were complex machines, and achieving optimal performance usually required patient refinement. Yet something unexpected happened. On a September morning, only days before the first official observing campaign was scheduled to begin, a signal appeared, strong, clear, and unmistakably gravitational in shape. The event, later named GW-1500914, marked the first direct detection of gravitational waves. Years of planning and decades of technological development converged in that one moment. Engineers, analysts, theorists, and observers contributed to a detection that validated general relativity and opened a new field of astronomy. LIGO's success demonstrated something broader than technical achievement. It showed how large-scale collaboration can turn what once seemed impossible into an accessible tool. No single team, institution, or nation could have built LIGO alone. Progress depended on a fusion of precision engineering, theoretical physics, data analysis, and international cooperation. Since the first detection, LIGO's instruments have only grown more sensitive. With each improvement, quantum noise reduction, better thermal control, enhanced mirror technologies, new layers of the universe reveal themselves. Events that once seemed beyond reach now appear regularly. Black hole mergers, neutron-star collisions, and more exotic compact objects contribute to a catalogue that expands year by year. The rise of LIGO now stands as one of the most ambitious scientific efforts of the modern era, not because it measured something small, but because it created a new sense of what is measurable. Certain scientific moments linger, not because they are dramatic, but because they are unmistakable. The first confirmed gravitational wave detection, GW-1500914, belongs to that category. The signal did not arrive with fanfare. It appeared quietly in the data stream at a time when the detectors were still being tuned. No announcements were expected, no analyses were underway. Yet the curve that rose on our screens carried the unmistakable signature of two black holes spiraling, together more than 1 billion years ago. It was the kind of event that needed no introduction. The signal's character speaks for itself. At first, the oscillations were low and widely spaced. As time progressed, the waves grew closer together, climbing in pitch and amplitude. This pattern, often described as a chirp, is the hallmark of a binary system losing orbital energy and drawing inward. Models built from general relativity had predicted this behavior for decades. Seeing it unfold in real data created a sense of recognition, not surprise, but confirmation. One of the remarkable features of that morning was the location of the wave's arrival. It first passed through a region near the Antarctic and then continued upward through the Earth, reaching the LIGO detector in Livingston, Louisiana. 7 milliseconds later, the same signal appeared in Hanford, Washington. That delay allowed researchers to determine a rough direction on the sky, though with large uncertainty. Even so, the consistency between the two detectors was unmistakable. Local disturbances do not appear in both sites with the same wave shape. A true gravitational wave does. Interpreting the event required careful analysis. Analysts compared the recorded waveform with thousands of templates generated from numerical relativity simulations. Each simulation described a possible merger scenario, different masses, different spins, different orbital orientations. The best match revealed that the colliding objects measured approximately 36 and 29 times the mass of the Sun. Their final combined black hole held about 62 solar masses. That difference, 3 solar masses, had been converted into gravitational wave energy during the last fraction of a second. To appreciate the magnitude of that energy, imagine compressing the entire mass of 3 suns into radiation and releasing it in a tenth of a second. The resulting power exceeds the combined luminosity of every star in the observable universe during that moment. Yet the waves reaching Earth barely altered distances by 1 part in 10 to the 21st. That contrast, unimaginable power, and vanishingly small effect reflects one of gravity's great subtleties. Even the most violent events in spacetime stretch our instruments only gently. Scientific caution demanded that every alternative explanation be ruled out before the result could be announced. Teams examined environmental sensors, checking for anything that might have mimicked the signal: seismic disturbances, magnetic fluctuations, equipment faults. More than 100,000 auxiliary data channels fed information into the analysis, and each potential source of noise had to be evaluated. The process took months. During that time, the collaboration treated the event with disciplined neutrality. Everyone understood the possibility of human error. As the evidence accumulated, confidence grew. No environmental disturbance matched the Beku shape, timing, or frequency evolution of the signal. No artifact in the detectors could reproduce the chirp. No known mechanism on Earth could generate identical waveforms thousands of kilometers apart. Eventually, the conclusion became unavoidable. We had observed a direct imprint of space-time dynamics from a distant corner of the universe. The announcement in February 2016 reached far beyond the scientific community. Newspapers placed the discovery on their front pages. The public responded with a mix of fascination and curiosity. Many were drawn not only to the physics, but to the idea that the universe carries memories of distant events in the form of space-time vibrations. Students asked whether these waves could offer new insight into cosmic history. Journalists asked whether the signals resembled sound. In a limited sense, they do. If converted to audio frequencies, the oscillations fall within a range that the human ear can interpret. This has no physical meaning. The waves do not produce air pressure, but the sonification provides an intuitive way to experience the data. From a scientific perspective, the first detection opened more than one door. It validated key predictions of general relativity, confirmed the existence of binary black hole systems, and demonstrated the capabilities of the detectors. It also established gravitational wave astronomy as a practical discipline. Before GW 150914, the field was defined by preparation. After it, the field became observational. The event also reshaped how researchers think about black hole formation. Prior to this detection, astrophysicists debated whether such massive binary black holes could form in sufficient numbers. GW 150914 showed that not only do these systems exist, they can merge frequently enough to be observed. Stellar evolution models have since been updated, and attention has shifted toward understanding the environments in which such binaries originate. Dense star clusters, isolated binary systems, or perhaps even more exotic channels. Patterns emerge when enough signals accumulate. After the first detection, gravitational wave astronomy quickly shifted from the excitement of a single event to the steady rhythm of repeated observations. Each new signal expanded our understanding not only of black holes and neutron stars, but of the population of compact objects scattered across the cosmos. In a sense, gravitational waves began to function like a new kind of cartography, one that does not rely on light, color, or chemical composition, but on motion, mass, and the geometry of space-time itself. A clearer picture formed as detections multiplied. Some events resembled the original black hole merger, pairs of heavy compact objects spiraling inward, merging with a final crescendo and leaving behind a remnant black hole slightly smaller than the sum of its parts. Others deviated. Certain mergers involved lower mass black holes, some with unusual spin alignments. A few appeared to contain objects heavier than any known neutron star, yet lighter than any previously observed black hole. These intermediate masses fell into what astrophysicists sometimes call the mass gap, a region long suspected to exist but never directly confirmed. Gravitational wave data forced theorists to re-examine assumptions about how stars evolve and collapse. Another category of signals revealed the internal structure of neutron stars. When two neutron stars circle closer together, tidal forces deform their shapes slightly. That deformation leaves a subtle signature in the waveform, one that depends on how compressible neutron star matter is. Observations such as the 2017 merger, detected by LIGO and Virgo, and followed by telescopes across the globe, allowed researchers to infer the stiffness of nuclear matter under extreme densities. In ordinary laboratories, no experiment can replicate these conditions. The pressure inside a neutron star is far beyond the reach of particle accelerators. Gravitational waves provided the missing constraints. Some listeners might wonder what a map means in this context. It does not resemble a chart of stars or galaxies. Instead, it takes the form of statistical patterns. The distribution of black hole masses, the typical spin orientations within merging binaries, the rate at which such systems form across cosmic time, and the environments likely to host them. Observing many signals allows astrophysicists to identify these patterns. With each new detection, the uncertainties shrink. It becomes easier to rule out certain formation channels or to favor others. Dense star clusters, for example, can bring objects together dynamically. Isolated binary systems evolve more gradually. The relative weight of these pathways becomes clearer as the catalogue grows. Long-term observing also provides insight into the expansion of the universe. Mergers of neutron stars emit both gravitational waves and electromagnetic radiation. If astronomers can measure the distance from the gravitational wave signal and the redshift from the accompanying light, they gain a direct method of estimating the Hubble constant, the rate at which the universe expands. This approach bypasses certain assumptions used in traditional distance ladders and offers a promising route toward resolving disagreements between existing measurements made using supernovae and the cosmic microwave background. Another layer of the map comes from future instruments. LIGO and Virgo represent the first generation of gravitational wave observatories capable of detecting stellar mass black hole mergers. The next phase, Cosmic Explorer in the United States and the Einstein Telescope in Europe, will push sensitivity significantly deeper. With improved isolation systems, longer arms, and more advanced quantum noise suppression, these detectors could observe waves 20 times fainter than those detectable today. A 20-fold increase in distance translates to nearly 10,000 times more observable volume. The sky would no longer yield a few events per month, but potentially dozens per day. That volume changes the scientific landscape. Detecting every merger of black holes below 100 solar masses within most of the observable universe would create a data set large enough to test subtle features of general relativity. Researchers could look for tiny deviations in waveforms, search for unexpected populations of compact objects, and study how merger rates evolved over billions of years. It is difficult to appreciate the scale of that shift without imagining a world where gravitational wave alerts become as routine as weather reports. Even more transformative are the signals expected from space-based detectors. The Laser Interferometer Space Antenna, LISA, planned by the European Space Agency, will focus on gravitational waves with much longer periods, minutes to hours rather than milliseconds. These waves arise from vastly different systems, supermassive black holes orbiting each other in distant galaxies, compact white dwarf binaries inside our own galaxy, and possibly cosmic strings or relic signals from the early universe. LISA's version of the gravitational wave map will extend across timescales far beyond the reach of ground-based observatories. Combining all these instruments produces a layered cartography. Ground-based detectors capture the final seconds of violent mergers. Space-based detectors trace slow in spirals over years. Pulsar timing arrays measure gravitational waves of still longer periods, years to decades, generated by enormous systems. And ultimately, the cosmic microwave background may hold the faint imprint of primordial gravitational waves from the first instant after the Big Bang. Each layer reflects a different era of cosmic evolution. In this emerging map, you and I see not a picture of where objects are, but a picture of what the universe is doing. We hear how stars end, how black holes form, how galaxies shape their cores, and how space-time responds to mass and motion. The signals reveal a universe in motion, not static but dynamic, filled with collisions, spirals, and quiet drifts. With each detection, the map gains resolution. The unknown regions shrink, the questions sharpen. Long before the first stars formed, before galaxies assembled, before atoms existed, the universe moved through a series of transformations so rapid and so extreme that ordinary matter could not record them. No telescope, no matter how advanced, can see directly into these earliest moments. Light simply did not propagate in a usable form. If we want to understand the universe at its beginning, the birth of forces, the emergence of structure, the instant when space itself expanded dramatically, we must rely on something that predates light as a messenger. Gravitational waves offer that possibility. The earliest waves likely originated during a phase known as inflation. According to many cosmological models, the universe underwent a brief but extraordinary expansion when it was less than a trillionth of a second old. During this expansion, quantum fluctuations, tiny random variations embedded in space-time itself, could be stretched to astronomical scales. Some of those fluctuations manifested as gravitational waves. By the time the universe cooled enough to emit light, these waves had already traversed vast distances, leaving subtle imprints behind. One way to detect those imprints is through the cosmic microwave background. This faint afterglow, mapped in exquisite detail by satellites such as NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission, carries information about conditions roughly 380,000 years after the Big Bang. Although gravitational waves do not leave visible ripples, their passage influences the polarization pattern of this ancient radiation. A specific swirling pattern, sometimes called B-mode polarization, could signal the presence of primordial gravitational waves. Researchers have been searching for this pattern for years. Some early claims proved premature, as dust in our galaxy created similar signatures. Current experiments continue to refine their sensitivity, and the question remains open. Another source of early universe gravitational waves may come from phase transitions in the fundamental forces. In ordinary matter, phase transitions are familiar. Water freezes, metals melt, gases condense. In the early universe, phase transitions involved entire forces acquiring distinct identities. For example, the electromagnetic and weak nuclear forces were once unified. As the universe cooled, they separated, a process that could have generated bursts of gravitational waves. The details depend on how rapidly the transition occurred and whether it produced expanding bubbles of the new phase. If such bubbles collided, they would have stirred space-time in ways that modern detectors might someday observe. Space-based observatories like the Laser Interferometer Space Antenna are particularly well suited for this task. LISA will measure waves with periods of minutes to hours, a regime where some predicted early universe signals may reside. Unlike ground-based detectors, which struggle with seismic noise at low frequencies, a space mission avoids Earth's disturbances entirely. If the early universe produced waves in the right frequency range, LISA could detect them as faint, persistent backgrounds rather than sharp, isolated events. Detecting such a background would be a profound step, akin to hearing an echo from the universe's first second. A still more distant target lies in the concept of the Big Bang Observer, a proposed future mission that would operate with sensitivity far beyond current plans. This instrument would aim to detect waves with frequencies of a few cycles per second, far different from the very slow waves seen in cosmic background studies and far slower than the rapid signals measured by LIGO. Such waves, if they exist, would be relics of processes that unfolded almost instantly after the Big Bang. Predictions remain uncertain and theoretical debates continue. Some models suggest strong signals, others predict none. Cosmologists treat these scenarios cautiously, aware that the earliest epochs remain speculative territory. Despite the uncertainties, the motivation to pursue primordial waves is compelling. They would provide information about energy scales unreachable by any particle accelerator on Earth. The Large Hadron Collider probe's energies trillions of times weaker than those present during the universe's infancy. Even the most powerful machines humanity might imagine building could not match the conditions of the first moments after the Big Bang. Gravitational waves, however, carry information directly from that era. They require no intermediary matter and no electromagnetic signal. They are relics of the geometry itself. Another advantage is that gravitational waves travel through the universe largely undisturbed. While photons scatter, absorb, and re-emit many times before escaping their surrounding plasma, gravitational waves propagate almost freely. That property makes them ideal messengers from eras that light cannot probe. If a wave formed within the first fraction of a second, its pattern today would still retain the essential structure of its origin, altered only by the expansion of the universe stretching its wavelength. Efforts to detect primordial waves extend beyond future space missions. Teams using pulsar timing arrays, networks of precisely monitored millisecond pulsars, have already reported evidence of a gravitational wave background at nanohertz frequencies. The signals they detect likely originate from supermassive black hole binaries rather than the early universe, but the technique proves that extremely low-frequency gravitational waves can be measured from Earth. Over time, improved observations may separate astrophysical backgrounds from potential cosmological ones. If primordial waves are eventually confirmed, they would reshape our understanding of cosmic origins, the physics governing inflation, the unification and separation of forces, and the earliest structure formation would move from theoretical prediction to observational science. Those waves would not be images or spectra, but patterns in space-time itself, memories preserved since the universe's first heartbeat. One thing becomes clear when you follow these threads long enough. The universe is not silent. It moves, it curves, it rings, and those motions leave patterns we can measure with increasing care. You do not need to witness a black hole directly to understand its presence. You only need to observe how it shapes the world around it. Light spiraling, matter heating, waves spreading outward across billions of years. The same principle applies to gravitational waves. They are faint, but they persist, and their persistence carries meaning. What stays with me after revisiting all of this is how much collaboration matters. The theories began with individuals, yet the discoveries required thousands of hands. When LIGO heard its first signal, The wave had already traveled more than 1 billion years. It waited for detectors precise enough to notice it. It waited for scientists patient enough to refine those detectors. It waited for a world willing to invest in understanding something subtle and distant. And eventually, the observation arrived, not as a sudden revelation, but as the natural outcome of collective effort. As we close this exploration, I want to leave you with a quiet idea. Every measurement we make, whether through light or gravity, connects us to events far beyond our lifetimes. When you listen to gravitational waves, you are hearing motion carved into space-time long before Earth existed. That perspective does not diminish our place in the cosmos, it expands it. And I'm grateful you chose to spend this time exploring it with me.